Okay, so now that we've studied integration, right, specifically we've studied indefinite integrals and definite integrals, and we understood the geometric intuition for what they are. Let's talk a bit about some physical applications. So these applications like a capacitor, you won't need to know what they are right now, but I'm just trying to highlight to you that even even though you do not know the context that they appear in, you can already perform these integrals. And the reason why I want to do this is because I want to separate the math from the physics. I want to try to separate them so that you can purely focus on the math, and you can realize that these integrals are easy to do in the math side. And when you look at the physics, right, you can focus more on the physical intuition, and you won't need to worry about, oh, how do I perform this integral, right? You realize that, hey, I've already seen this integral when I talked about the math, and so now I'm just focusing on understanding the physics behind it. So the first one will be the energy in the spring, right? Basically, we're integrating some constant k times r, and we're integrating with respect to r. Remember, this dr tells me what variable I'm integrating with respect to. So if I integrated with respect to k, if this was a dk over here, then the answer would be different. So it is important to write over here d, the variable they're integrating with respect to. So if I integrate this, we see that k is a constant. So integral of r is just half r squared. So this is half k r squared plus c evaluated at the endpoints x and 0, x being a constant, right? So you also see that previously we treated x like a variable that we integrate with respect to, but in this case r is the variable that I'm integrating with respect to. I could have very well renamed r, let's say q, so I could have written integral of 0 to x kq dq, right? That also gives you the same result as integral of kr dr. In other words, r is kind of like a dummy variable that you can change the name to, because after that you're integrating over it, so it wouldn't appear in the final expression. So yeah, so basically what I'm trying to say in this example is just that don't be too attached to having certain variables be your variables, your variables that you're integrating with respect to, because it depends on the context. In this context, x is just a constant, and in fact I'm integrating with respect to over the two endpoints, r equals to x and r equals to 0. So r in this case is the variable, whereas x is just a constant. And in general, that applies for all of physics, right? You need to know when things are constants and when things are not constants, when things are variables. So anyway, evaluating at this expression at r equals to x and r equals to 0, I get half k x squared plus c minus, when I substitute r equals to 0 into the expression, I just get c. So of course the c cancels out, and I'm just left with half k x squared. So this is the energy in a spring, and this is actually the force, and this is actually distance. So before I even talk about force, distance, and the work energy theorem, we can already see that there's some idea of force times distance is equals to work, right? And this is the work done into compressing or stretching the spring. But we'll talk more about that in the future. So next is the energy in the capacitor. Very similar to the above example. In fact, mathematically kind of identical. Just that instead of multiplying by a constant k, I'm dividing by a constant c. C is going to be the capacitance, which we'll talk about in the future, but I just want to focus on the integral for now. So this will give me half q squared over c plus, in this case, I cannot name my constant c because c is already used to denote capacitance, so let's just call it d. And I'm evaluating at the two endpoints q and 0. And this will give me big Q squared over 2c. So this is the energy in the capacitor, and this is kind of like the work done in taking a small charge and moving it from one end of the capacitor into the other end of the capacitor. So in other words, I'm basically, to charge up a capacitor, I'm kind of moving a small amount of charge, right? Initially from 0 charge, right? And I'm moving it until it accumulates a total charge of capital Q. So for each amount of charge dq I'm moving, right, the energy required is Q over C, because that's the voltage across the two ends of the capacitor. So yeah, don't worry if you don't understand that. I'm just trying to give a bit of physical context for what we're doing when we perform this integral. But we'll go into electrostatics a lot more in future. So okay, that's the energy in the capacitor. Lastly, for gravitational potential, right, we're integrating with respect to dx, that function 1 over x squared, from x equals to r to x equals to infinity. So previously we did cover the integral of 1 over x squared, and we saw that is minus 1 over x plus c. So we can just use that, minus 1 over x plus c, but we know the c cancels out already, so over time you wouldn't write it. And we're evaluating it at x equals to infinity and x equals to r. So x equals to infinity actually isn't a well-defined, mathematically you actually need to take the limit and stuff, but for our purposes, for physics, if you substitute x equals to infinity into the denominator, you get 0. So this is just 0 minus negative 1 over r, and this is 1 over r. So this is kind of like the gravitational force, right? This is a distance, and this will give me the gravitational potential. So this is another instance of the work energy theorem, which is very similar to what we saw over here. In other words, the amount of energy, the amount of potential energy that a system, right, could be a spring, could be a gravitational system, but the amount of energy that a system holds is the integral of the force with respect to distance when you go from one point to another. So if you apply some force to a particle, right, and move it along some distance, you're kind of storing the energy you're kind of storing the work that you did in the form of a potential energy of the system. Yeah. But if you didn't understand that, it's okay also, because we're just talking about the math here. Okay, so with that out of the way, we have covered integration, differentiation, and now we're ready to move on to kinematics.